Hello, guys. Welcome again to this lovely session of Electro-technics Engineering. Today, guys, we'll be doing Electro-technics N5. We'll be doing the first chapter of the book, which is DC machines. Okay, so Tina will be doing EMF equations of uh, direct current machines. Okay, please guys, do like and subscribe to the channel, and also share the channel to other students, to your fellow classmates, so that they can also get this assistance that you guys are also getting through this channel. Please guys, do share the channel. um as I've said, today we'll be focusing on the EMF equation of DC machines. Okay, so the chapter is about DC machines. Okay, and in electrical, guys, we know there are two types of machines, of electrical machines. Those two type of machine are motor and indoni and the generator. Okay, those are the two types of electrical machine that we'll talk about in electrical engineering. There's no other machine that we talk about. Whether it's AC machine, we're still looking at a motor and a generator. Okay, so before I start with this chapter, firstly we need to know the difference between a motor and a generator. A motor converts electrical energy into mechanical energy. So a motor converts electrical, E means electrical, to mechanical. M means mechanical. Meaning, guys, the input power to a motor is what? Electrical. Then the output power in a motor is what? Mechanical. This is going to be very important, guys. Then in terms of the generator, guys, the generator does is the opposite of what the motor does. The generator converts mechanical energy into electrical energy. Okay, so meaning which, guys, in a generator the input power is mechanical, then the output power is what? Electrical. That is the difference between a generator and a what? And a motor. But both of these, we refer to them as what? Electrical machines. Okay, and notice the chapter, guys, is saying DC machines. It means these two machines operate on the principle of direct current, meaning which we must supply a motor with a direct current electricity for it to give us motion. In terms of the generator, it means that we drive the generator mechanical for it to give us direct current electricity. Okay, so that is the introduction, guys, to this topic. So now that is the difference between a motor and a generator. Okay, moving on, guys, let us look at the EMF equations that I'm talking about. Let us look at the EMF equations. Okay, so I'm gonna split this board in half. Okay, This side, I'm going to talk of a motor. And this side, I'm going to talk of the generator. Okay. So I'm going to start with the equation that perhaps most of you guys know from N4. Okay. This equation, guys, it applies to both the generator and the the uh, the generator and the motor. It applies to both type of DC electrical machines. Okay, we can say it's a universal equation. So this equation goes as E is equals to 2 K over 60. And notice that I'm writing it also on the generator side. Okay. Sorry, I forgot the C there. You see, these are the same equation. Okay, this is the same equation. This equation, you can use it for a generator or you can use it for a motor. Okay, the only difference is that, guys, E in a motor is the E is the back EMF. Okay, then in a generator, E is the E is the E is the generated EMF. Okay, that's the difference between them. And also N is the speed at which the motor the speed at which the speed at which the motor what runs. Okay, that we can control it electrical. You'll see when you're doing speed control of DC motors. Then N here in terms of the generator is the speed at which the generator is what driven. Is the speed at which the generator is what driven to produce electricity. Notice the difference in a motor. N is the speed at which the armature or the motor runs, but in terms of the generator, it is the speed at which the generator is what driven. Okay, and guys, another thing, OP is the pole pair, we know. Then that is the flux. Then OZ is the number of armature conductors. Yeah. Then, guys, C, in terms of C, we know that is the type of armature connection. There are two types of armature connection. That is the wave and lamp. Of which is, if it is a wave, we say C is equals to 2 only. That is for a what? A wave. Okay. Then if it is a what? If it is a lamp, C is equals to 2P for lamp wound armature. Okay. So this is the universal equation. Okay. Then another EMF equation. Can I please just wrap here? Another EMF equation. This one is for a specific machines. Okay, these equations are not universal. One is for a what? One is for a generator. One is for a what? A motor. Okay, so guys, let me start with the motor's equation. And when when you are dealing with the motor, I want you to think of a minus. When we are dealing with a generator, I want us to think of a positive. Okay, so if I'm gonna write this equation to calculate the back EMF is goes like E is equals to V minus voltage drop across the armature circuit minus the voltage drop across the armature circuit. So you'll see when I'm doing the example, what do I mean? The voltage drop across the armature circuit. And OE, we said in a motor, is the back EMF. No? Then if you see this equation is derived according to Kirchhoff's law, Kirchhoff's voltage law. Hence, these equations are specific to this equation is specific to a motor. Okay, you cannot use this equation to a generator. This one is not universal, it's specific for a motor. Where V is the supply voltage. Remember, remember guys, we supply a motor with what? Electricity for us to get motion as what? Output. So V is the supply voltage. Okay, then in terms of the generator, E is equals to V plus voltage drop across voltage drop across voltage drop across the armature circuit. Voltage drop across the armature circuit. Notice I'm saying plus there. Okay, and we know, as I said it earlier, that E in a generator is the generated EMF. Okay, then V here in this case is the terminal voltage, or what you call the output, the output voltage. Remember now we are generating here. We are generating. No? That is E. No? Then before I start doing an example, I want us to clarify something, guys, with regards to power. I want to clarify something. People, they always have a confusion on this. Okay. There are two types of powers in electrical machine. One is electrical power and what? And mechanical power, as I mentioned in the beginning of the video. Electrical power and what? Mechanical power. Okay. In electrotechnics, guys, this is an electrical subject. So there is no formula to calculate mechanical power in electrotechnics. Let me put it like that. No formula to calculate mechanical power. Instead, we will manipulate if we need to use mechanical power. Then the formula for electrical power, you know from N4, the formula for electrical power is V times IL, where IL is the load current. Okay, but now you must be able now to differentiate between the motor and what? Generator in terms of power. Must be able to differentiate between the two. Before I start differentiating, we know efficiency is calculated as power out over what? Power in. And that's how we use the manipulation. So, guys, in a motor, we said earlier in a motor, input power is what? Electrical. So basically, if input power is electrical in the motor, it means power in a motor is V times what? IL. Then power out, we have what? No formula in a motor. Then in a generator, guys, what is electrical in a generator? The output power, it means now V times I belongs to the output power in this case. And there is no formula for the input power. Okay. And most of the time, the formula, the power that you will be using, the power that you use is electrical power in calculations. It's what? Electrical power. Okay. And the given formula, the given power, if you are just given power, the given power, you always take it as what? Output power. You know that. You know, guys, you know that. Given power, you always take it as what? Output power. Unless the question specifies it to you that this is the power drawn. The power drawn, it means that is the input. Okay? You always take it as the input. For example, let's say I'm given an output power and the question is talking about a what? A motor. So, and I have to find the load current. I cannot use V times I on that power, the output power. I need to manipulate, and usually I normally say to my student, what gives you a hint is they always give you the efficiency so that you can manipulate to get what? The input power. And if you have to convert the power, they will give you the efficiency. That means I need to convert this power because it's what? It is mechanical. It is not electrical. That is why the examiners give you the efficiency, because you every time you are given the efficiency, it means you must know that that is a hint that I have to convert this power. Okay, guys. Now we are going to do calculations. Né? We are going to perform some calculations. I'm gonna first read through the whole question. Okay, as you look it up on the screen. The question goes as follows: a 6-pole Lampoon 350 shunt excited DC machine draws an armature current of 7.5 amps at no load and runs at 1,300 revs per minute. When loaded, the motor draws an armature current of 70 amps from the supplies and runs at 1,300 revs per minute. The resistance of the armature circuit is 0.6 ohms and there are 1,100 armature conductors. Calculate the following for loaded conditions. They want us to calculate the generated EMF. They want us to calculate the useful flux per pole. Then the last question wants us to calculate the useful torque developed by the machine in Newton meters. Okay, guys, I'm gonna run the question again so that we can write our givens. No? Okay, so we are told that this is a 6-pole, meaning P, the pole pair, is equals to 3. Okay, you simply just divide the total number of poles by 2 to get the pair. And we are told this is a lamp wound, meaning C is equals to 3 times what? 2. Remember, I said for a lamp wound armature, C is equals to 2. C is equals to what? 2P. So the 2, you simply multiply the pole pair by 2, of which is C will be what? 6. And we are told that this is a shunt excited DC machine. Okay, and they say it draws an armature current of. So guys, the fact that they say this machine draws current, it should indicate to you that this is a what? We are dealing with a what? A motor. A generator does not draw current. A generator delivers current. Okay, so we are dealing with a motor because we have a machine that draws, and we are told that this is a what? A shunt, meaning this is a shunt motor, shunt excited motor. Okay, remember again, you know from N4 that there are 3 types of DC machines. That is a series, a shunt, and a compound. Okay, just to quickly draw the shunt, since we are talking of a shunt in this question, you have the field winding in parallel with the armature. Okay, and since this is a motor, current is being drawn from the supply. This is the supply mass. Okay, current is being drawn, so we'll have IL here, then IA, then I shunt. This is how current flows in a what? In a motor. But in a generator, the current originates from the armature and it's being delivered. It is not being drawn. Okay. What else? Okay, we are told that it draws an armature current of what? IA is 7,5. But now the question is telling us this is occurring at what? No load. Okay, no load means, guys, the motor is not driving anything. It's not driving any mechanical load. It's just running on its own. Okay, and we are told that the speed at this no load condition is what? 1,300 revs per minute at no load. Okay, then the question continues. They are loading. They say when loaded, meaning there's something now. The motor is driving a mechanical load. It could be driving anything. It could be driving a locomotive. I'm just making an example. That motor is used to drive a locomotive, or let's say it's a fan motor. It is spinning the blade of the fan. It is loaded. Something is attached to the shaft. Okay. Then they say when loaded, the motor draws an armature current of IA, which is equals to 70 amps when loaded. Notice I'm writing these things down, okay? Because statement is very important in electrotechnics. That is why people make mistake. They don't pay attention to detail. Uh, Let us continue. It draws 70 amps from the supply and it runs at 1300 revs. You see, it's still running at the same speed during when it is loaded, and it is still running at the same speed as the time when it was at what? No load. It's still running at 1300 even when loaded. Okay. Uh, then they say the resistance of the armature circuit is 0.6. So RAC, armature circuit, is 0.6 ohms. And there are 1,100 armature conductors, meaning Z is equals to 1,100. Okay, now let us do the solution. Let us do the solution. Okay. The first question wants us to calculate the generated EMF, which is the back EMF, guys. E, we said for a motor. Okay. There are two formulas before I start calculating. There are two formulas. Let me write down. There's a general one, the universal formula, 2p z, 2p flux z n over 60c. The problem with this one, in this case, we don't have the useful flux. So I cannot apply this formula because I don't have any the useful flux. Useful flux is the one that they want us to calculate in the follow-up question. Okay, so that means I'm only remaining with this formula, the specific EMF equation. I'm only remaining with this one, which is the voltage drop across armature circuit. The voltage drop across the armature. That is the only formula that I can apply. Okay, so I'm going to use that formula because I do have the supply voltage. Okay, and I can calculate the voltage drop across the armature circuit. Remember, according to Ohm's law, a voltage drop is equals to the current times the resistance. I have the armature current when loaded. Remember, the question wants us to do this calculation for what? Loaded condition. Okay. The armature current for loaded condition, we said it's what? 70 amps. Okay. That is for loaded condition. They want us to find the EMF for loaded condition. Then the resistance of the armature circuit I also have. The resistance of the armature circuit, we are told it's 0.6 ohms. Yeah? Okay. Then I have everything to calculate the back EMF or this generated EMF because I have the supply voltage. Did I write it down? I forgot to write it down. The supply voltage was, 350 volts. So in my calculation, I'm going to say 350 minus 70, open bracket 70. That is the current. Remember, the voltage drop across the armature is going to be IARAC. because the voltage drop, according to Ohm's law, is a function of current and resistance, of which is the current during a loaded condition. The armature current is 70 amps. Then the armature circuit resistance is 0.6. So, okay, guys, I should get the back EMF as 308 what volts. That is the back EMF. So, guys, because I'm gonna require more space, I'm gonna ask just to erase here, just to erase. Okay. Okay. That is the back EMF. The next question wanted us to find the useful flux. The useful flux, of which is I can now apply this general EMF equation because I do have the back EMF, I do have the pole pair, I do have OZ, I do have the speed, I do have C. So if I'm going to manipulate that formula, I find that the formula for the useful flux is going to be E times 60 C over 2P Z N, of which is E for a loaded condition is what? 308, sorry, 308 times 60. C, we said C is what? Because it's a lamp wound, we said C is what? 6 over 2. P is 3. Then Z is 1100. Then the speed when loaded, during the loaded condition, the speed when loaded is still that 1300 revs per minute. Then the flux should be 12,923 milliwebers, the useful flux. Okay, then the final question wanted us to calculate the useful torque in what? In Newton meters, of which is, guys, the torque, the formula for the torque, this is for the torque for a DC motor. This is the formula for a torque for a DC motor, 0.318 IA, then the flux, then Z, okay, then P over C. Okay, so I do have the armature current, I do have the flux, I do have Z, I do have P, I do have C. So that is gonna be 0.318. The current when loaded. Remember, the question specified for loaded conditions. That is why I'm always using that 70 amps. If it said calculate for no load condition, then I was going to use that 7.5 amps because that is the armature current at no load. Guys, you must pay attention to detail. Okay, so 70 times 12,923 times 10 to the power minus 3. We calculated most the useful flux to be that, times Z, which is 1100, times P, which is 3, over C. C is what? 6. Then I should get the torque as, the useful torque as 158,216 Newton meters. Okay, so we did this question. Then we'll look at another question.